Welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. This is the first class I'll be taking. So in the first class we'll be discussing about the Maxwell equations. Maxwell equation, the four most powerful equation in electromagnetic field theory. We'll try to understand the Maxwell equation in integral form, differential form, and also try to understand what a physical meaning behind all these Maxwell equations. And in order to understand advanced electromagnetic field theory, you need to understand these Maxwell equations completely, thoroughly. So let's start with the first Maxwell equation. The first Maxwell equation is Gauss law for electric field. So what is the first Maxwell equation? Gauss law for electric field. The integral form, we can write it like d dot ds is equal to rho b dv. So in the left hand side, what do we have? D is the electric flux density. So you are doing a surface integral of electric flux density over a closed surface. So you have a circle in the integral. Circle in the integral says that this is a closed surface. You are doing integral of electric flux density over a closed surface. So electric flux density, you multiply with the area, you get the electric flux. So basically d dot ds in the left hand side over a closed surface gives you the electric flux which is coming out from the closed surface, and it is equal to whatever you have on the right hand side, rho b dv. Rho b is the volume charge density. You integrate the volume charge density over a volume. What do you get? You get the charge. So basically electric flux which is coming out from a closed surface is equal to the charge enclosed by that closed surface. So you can also write this in a differential form by using vector analysis. What you have is divergence of electric field equal to rho b by epsilon. So electric field always has some significant divergence which is related to the volume charge density and epsilon. So let's look at the physical meaning of this first Maxwell equation, which is also called as Gauss law for electric field. Physical meaning you can interpret from the integral form the Maxwell equations first law. So basically it says that the electric flux through any closed surface is equal to the algebraic sum of extraneous charge embraced by this surface. So we have discussed about the first Maxwell equations, which is Gauss law for electric field in integral form, differential form, and we have also discussed about the physical meaning behind this Maxwell equations. Let's go to the second one. The second one has something to do with the magnetic field. We call it Gauss law for magnetic field. The integral form is b dot ds is equal to 0. B is magnetic flux density. When you integrate it over a closed surface, integration with a circle here basically means that you are integrating it over a closed surface. When you integrate magnetic flux density over a closed surface, you get 0. So that means basically means that magnetic monopoles doesn't exist, and magnetic field lines are always continuous. Unlike the electric field lines, it doesn't have a starting and ending. So in the differential form, you can simplify it using the vector analysis. It gives that divergence of magnetic flux density is equal to 0. Magnetic flux density doesn't have any divergence. Let's look at the physical meaning. It can be interpreted from the integral form. It says that flux of magnetic field through any arbitrary closed surface is always equal to 0, or in other words, magnetic monopoles doesn't exist. So second Maxwell equation has been discussed. So let's go to the third Maxwell equation. Third Maxwell equation was based on the Ampere's circuital law. Ampere's circuital law has some flow. Maxwell actually modified it, corrected it. What is that flow? We'll see in the next equation we have here. So the equation in the integral form is I dot dl is equal to j plus dou d by dou t dot ds. So left hand side you have a closed contour integral of magnetic field over a line, and in the right hand side you have a surface integration. So in the right hand side, let us look at it. You have j is the conduction current density, dou d by dou t is the displacement current. So this term is actually introduced by Maxwell. Without that, this equation is incomplete. So let's look at the differential form, and what do I have? Curl of H is equal to j plus dou d by dou t. So left hand side you have a magnetic field. Right hand side, what is the source for magnetic field? The first term j is the electric current density, which is the conduction current density. Second is the displacement current density. So look at this second term, dou d by dou t. It's a change in the time with respect to time of d. D is basically epsilon e. So basically what it means is when you have a time varying electric field, it will automatically produce a magnetic field. So physical meaning for this is, from the integral form you can make the interpretation, and it basically says that circulation of magnetic field vector around any arbitrary closed contour is equal to the total current through any arbitrary surface bounded by this contour. So if you have a closed contour, how many arbitrary surface it can make? It can make infinite surface. I'll discuss it clearly in the online class. So now basically your circulation of magnetic field vector around any arbitrary closed contour is equal to the total current. Total current means you have both conduction current and displacement current. Don't forget that we also have displacement current due to the time varying electric field, and we also have conduction current J. So total current through any arbitrary surface bounded by this contour. So let's go to the last Maxwell equation. The fourth Maxwell equation was by Faraday's law, and its integral form looks like this: E dot dl is equal to minus dou v by dou t dot ds. So basically left hand side you have a closed line integral E dot dl. So electric field is there in the left hand side. Right hand side, what do I have? I have a magnetic field which is time varying. So in a way you look at the differential form, curl of E is equal to minus dou v by dou t. So right hand side dou v by dou t means you have a time varying magnetic field. It gives rise to electric field. So this equation says that whenever you have a time varying magnetic field, electric field is automatically produced. The previous equation also says that whenever you have a time varying electric field, magnetic field is automatically produced. You cannot separate this electric field and magnetic field for the time varying fields. So this gives rise to what is something called electromagnetic waves. You will see that later on, using these two Maxwell curl equations, the third and fourth one, you can give rise to waves, electromagnetic waves. Very good phenomenon in the electromagnetic field theory. Finally, let's look at the physical meaning of this fourth Maxwell equation, which is also called Faraday's law. It says that circulation of electric field vector around any closed contour is equal to minus sign. Don't forget the sign, it comes from the Lenz's law, of the time derivative of the magnetic flux linkage through any arbitrary surface bounded by this given contour. So you can have any arbitrary surface, you can have infinite number of them. I have already told you in the previous case also. Here also, whenever you have a closed contour, you can form an infinite number of arbitrary surface. So that's the end of the fourth Maxwell equation. We have reviewed all the Maxwell equations. First one was Gauss law for electric field. Second one was Gauss law for magnetic field. Third one was modified Ampere circuital law. Last one is Faraday's laws. So these four Maxwell equations, you have to know it in integral form, differential form, and their physical meaning. That's all. Thank you.